This is the next video in the chapter on electronic structure and periodic properties. We have just spent a good amount of time talking about wave-particle duality of energy, about how energy and light can be modeled both as a wave and as a particle. And now we're going to show that that is also true for very, very small particles of matter. So first of all, here in our structure, our outline for the course, we talked about the quantization of energy last time. So we want to check that off in our atoms section of the plan and move on towards the electron configuration section. So we introduced this concept of wave-particle duality before when we were talking about light or energy. So light, also called energy, waves also have particle properties. It can be useful to model light as a particle. And that was already a pretty revolutionary idea. To think of light as both a wave and a particle was just a lot to take in. And now we're going to introduce the fact that we can do the same thing for very small particles of matter. So matter particles also have wave properties. You know, you might be thinking to yourself, why would I ever want to model myself or my book or my pencil as a wave? And the answer is you wouldn't. This is really only useful for very, very small sized particles. And so in 1925, this theory was introduced by a scientist named de Broglie in his PhD dissertation. And what he said was that microscopic particles, like electrons, are the ones that this theory is important to. Electrons are very, very small and very, very lightweight. So they are modeled the most accurately as waves, meaning they have all the other properties of waves that we saw before. So electrons can be modeled as waves, and to model an electron as a wave, we need to introduce another wave property for our list. Okay, so that property that we're going to use to model electron waves is whether that wave is considered a standing wave or a traveling wave. I feel like this is the lead up to a joke, but unfortunately I don't have a joke about traveling waves. We'll have to think of one. So, spoiler, electrons are standing waves. But let's talk about traveling waves first, because traveling waves are something you can probably think of an example of. If you've ever seen folks in a football stadium doing a wave or a wave on the ocean, that's an example of a traveling wave, because in a traveling wave, the energy moves with the wave. W/ indicating with the wave. So the energy is there, and then the wave moves on and the energy is no longer in that physical location. For example, this wavy line is supposed to represent water, like the ocean, and the ocean has some pretty large waves on it. And those waves physically travel in space. So the wave starts out on the left side of our ocean, it moves towards the right, and it continues moving all the way towards wherever that wave is going. And so if I was situated at a particular spot, maybe I was a little clam in the water, that's what that horrible picture is supposed to be. If I was located at a particular position, then as that wave moves past, at one point I would be at the bottom of a wave, then I would be at the top of the wave, in the middle of the wave, and at the bottom of the wave again. And no matter where I put that clam in the ocean, that clam would at one point be at the bottom, the middle, and the top of the wave as the wave traveled through that physical location in space. Now, when we're talking about modeling an electron as a wave, we are going to model it a little bit differently because electrons are sometimes traveling, but when they're situated around an atom or a nucleus, they are not traveling, they are stationary. And so we can model them with what's called a stationary or a standing wave, where the energy of the wave is stationary and it doesn't physically move on the x-axis through space. And so since the position doesn't change, what does change about the wave is its amplitude. The amplitude varies with time. And so the easiest example of this is if you think of two people holding a jump rope and they're moving that rope up and down and the rope is moving up and down in space while the ends are moving, holding fixed where those people are holding them. You can also think of a string on a stringed instrument like a violin that's fixed at either end wherever you put your finger and is vibrating in between. But I am not capable of drawing a violin. So instead, we are going to use the example of a microwave. Microwave is not an example of an electron wave, but it is an example of standing waves. We can use it as an example here. And I'm going to draw a horizontal line down the middle of my microwave to indicate where the 0 line would be in our imaginary axis, and to help me draw my wave. So here is a wave, a standing wave in a microwave. And one feature of a standing wave is that at the left and the right side, where you would imagine the person holding the end of the jump rope would be, those ends are fixed, meaning that they are sitting right at y equals 0, right on that axis going down the middle. And this wave moves in space. So at any particular point, the wave would sometimes be positive above the axis, and it would sometimes be below the axis, negative, and it would sometimes briefly be at 0 on that axis. And the energy would oscillate vertically rather than oscillating horizontally in space. And it's difficult to tell from this non-mobile picture, but I do have this picture that I've printed from a computer that might be helpful. So each of the different colored lines represent the wave at a different time in space. So the pink one is time equals 1, the orange one time equals 2, the green time equals 3, the blue time equals 4, the purple time equals 5, and this dark purple time equals 6. And so if you picked a particular point, like this point I've drawn here, as time goes on, that part of the wave changes in amplitude. It goes from positive amplitude through 0, down to negative amplitude, back through 0, back to positive amplitude. And it physically oscillates in the y direction over time. And so different points on the curve will oscillate by different amounts. The amplitude isn't always the same size, but most of these points will oscillate up and down over time. Now, the one interesting point here, you may have noticed, are these points here where all of the lines intersect on the axis. And at these points, the amplitude is always 0. The wave does not go up or down in intensity, and it does not leave the axis. The intensity at those points are always 0. We can see 1, 2, 3, 4 points like that. And those points are special features of standing waves that traveling waves don't have. Those features are called nodes. So nodes are interior points on standing waves only that are not in motion. So when the wave is moving or the jump rope is vibrating, that point is not moving. So we could say that the amplitude at these nodes is always going to be 0. There's no wave intensity here. And in our little microwave picture that we drew, we can see that there are 2 nodes there. One here in between positive and negative, and one here in between negative and positive. The ends do not count as nodes. It has to be an interior point to be a node, so it has to be somewhere other than the left or the right side of the box. And you can think of these as cold spots in the microwave. When you microwave your food, sometimes there are spots in the food that are cold, even though parts of it are scalding hot, other parts of it are ice cold, and this is because there are nodes at some of these locations. This is the reason that your modern microwave will spin, and the reason that your TV dinner tells you to take it out at halfway and stir it in the middle is because some of these parts of the food that are located at nodes in the microwave don't actually get heated. And so an electron wave will look very similarly to this. It will be located within a fixed location. Most of them will have nodes where the intensity is 0, and they will oscillate over time. So you can use this as an example to help understand what a stationary electron wave would look like. And in the next video, we'll talk about the Schrödinger model, which assigns an equation to model what an electron wave would look like.